Welcome back as we continue with the control system for continuous processing on the subject of derivative control action. Before the break, we saw how our new two-mode controller solved the problem of an offset. But another problem occurred, again whenever one of the bottling lines was shut down or restarted. Several bottles of product were off standard right after a load change occurred. The problem was a large, but short period, temperature deviation from set point at the time that the load changed. This problem, called overpeaking or process overshoot, occurs when the load change is large and sudden, and it is a temporary problem. The reason for overpeaking is that the speed or rate of valve position changing is too slow. What the system needs is a device which can detect the rate of temperature change and then cause additional valve movement whenever a rapid change occurs. The device has to anticipate a rapid change effectively as sensed by the temperature error signal. Such a device is called a derivative action unit, sometimes called a rate of action unit. To help illustrate the concept of derivative action, imagine that a speedometer is linked to the temperature indicator. Let's then suppose that the more quickly the temperature indicator moves, the more the speedometer registers. A slow movement of the temperature indicator then results in a low speedo reading. No movement obviously results in no speedo reading. In effect, a derivative action unit senses the speed of temperature change and then adds a signal to that of the proportion unit, effectively causing additional valve position movement. As soon as the temperature is steady, the derivative action stops. Let's see how such a device works to overcome our problem of overpeaking. A load change occurs as one of the bottling lines is brought back online. The temperature drops due to the sudden load increase, and the derivative action unit responds by signaling the proportional action unit to give additional but temporary valve opening. The product temperature begins to stabilize and levels off, hence the derivative unit action will stop. Once more, the valve is positioned under the control of proportional and integral action. Our controller now has three modes, having added the derivative action unit. Optimum settings of the controller must be set and calibrated carefully by plant engineers or technicians. Our complete continuous process system is now under the control of a three-mode controller, or PID unit. In our simplified explanation of PIDs, we have been concerned only with one processing variable, namely temperature. Similar PIDs are also used to control other variables such as pressure, flow, levels of materials, and even some robotic operations. Control units, such as in our example, are often created using electronic components to monitor the system and to send the required signals to the final control elements, which is the steam valve in our case. Other controllers may use pneumatic or hydraulic components, but the general principles that govern their behaviors are all similar. PID controllers are examples of feedback systems, as each control unit depends upon a sensor, sending back information to a control device. Only then can the device analyze the signal and then send the necessary modified signal along to the final control element, which was the valve's actuator in our illustration. You will discover various designs and types of automatic process control systems in virtually all modern processing operations. Further advancements are being made almost daily as new production challenges are being met. In future programs, you will learn the principles of operation of yet more sophisticated controllers, all of which are aimed at creating plant efficiency, safety, and product quality. Join us again when you can learn more on the subject of control instrumentation and process control systems.